Hi, my name is Ross Kendall, and this is my project titled Fastening Studs by Welding. So studs are used as mechanical fasteners on target plates. So this is a very common practice in commercial and construction applications. But you could basically have a stud that would take on any form, and these are a bunch of examples. But you need to mechanically fasten them to a plate, and that plate could be, a beam, a wall, or any other place that you would want this stud attached to. And you could weld them on using a stud gun. And this is kind of what they look like after they've been welded on. You have the stud, you have the plate, and then you have the welded region in between that holds the two together. So I focused on two different types of stud welding techniques. One is the drawn arc stud welding. This is a very common practice at EB and throughout construction applications, but you're basically using electrical current to weld the stud to the target plate. So you have your stud that's surrounded by a ceramic ferrule, and it's pressed against the target plate, and you send that current through the whole system. And then you take that stud and you lift it away from the plate, and you create this arc to form between the stud and the plate. And what that does is it creates a large amount of energy, and it heats up the bottom of the stud and the top of the target plate. So you create this molten region where you then plunge the stud down into, and you basically allow that to cool, and then you have your welded stud attached to your plate. Another type is friction stud welding. I did a lot of research on this for this project, simply because this can be done in places that drawn arc welding cannot, specifically underwater. You can imagine being underwater, you don't want electrical current to pass through your system. So this friction stud welding is a way to get around that. So basically, instead of using electrical current, you're using friction to create your heat. So you have this motor that rotates or vibrates your stud back and forth as you apply pressure down, and you're creating friction between the bottom of your stud and the top of the plate that will then heat and coalesce, and then you basically take off that motor and you allow it to cool, and you create your welded stud. So this is a really cool technology that I focused on for my project. But for the focus of modeling purposes, I specifically looked at drawn arc stud welding. So one common issue that we come up with at work all the time, I work in the non-metallics groups and work with a lot of temperature sensitive materials that are bonded to a steel surface. And you can imagine if you're welding studs onto that same steel surface, you're going to create a lot of heat. And a lot of the engineers want to know, how far away does this stud need to be so that you don't degrade your materials that are temperature sensitive. So this is a question that comes up a lot, and it's one that I try to answer using this project, as well as to create a thermal model for the drawn arc stud welding process. So to create my model, I selected corrosion resistant 316L stainless steel stud and the target plate. So they're both comprised of the same material. This is the chemical composition of the stainless steel, as well as some non-constant material properties that I used, the effective heat capacity and the thermal conductivity. Note that for both of these, there's a specific value for the melting range, which is 1644 Kelvin to 1672 Kelvin. So that's just to show that there's different properties during that melt phase, which is obviously true. So for the model development, I created a 2D axisymmetric transient heat transfer in solids model. I got recommendations from a vendor. Basically, when you go to weld a stud in real life, you plug in a bunch of parameters into the gun, and it kind of does the rest for you. So this vendor who makes this gun gave me these parameters for a 1/4-inch diameter stud, which is what I'm going to focus on for this project. And I created this geometry. So you have your target plate on the bottom here. You have your stud with there's a head of the bolt, and then you have a ceramic ferrule that kind of guides this thing down. One thing I want to note is this lift distance. This is going to be important for a lot of this. That lift distance is this distance between the bottom of the stud and the top of the plate. So for the model, this is the heat equation. This is a generalized heat equation that governs all heat transfer in solids. But the two boundary conditions, one is your heat source, which is going to be that electrical current, which is just the definition of power, which is your current times your voltage. That's your Q in. And then surroundings is just Newton's law of cooling, showing that some heat is lost to your surroundings. So I approached the stud welding model in I took two different approaches. One is I used a boundary heat source. So basically just in that region where the stud would come in contact with the target plate, I created a boundary heat source here and had all that heat source from the electrical current be created in this region. And then all other boundaries just use that natural convection Newton law of cooling. And then the second approach that I used was this plasma region heat source. So if you ever see a drawn arc stud welding process, you'll see this really bright light when they do it. And really what that is the nitrogen region in between the plate and the stud heats up rapidly, and you create this nitrogen plasma. So in this area, I created a nitrogen plasma region where the properties of this material in here is the properties of a nitrogen plasma. And then the heat source was created in that area. So these are the two results I got for each one, and we'll talk about them further. Talk more about them further, but just wanted to show that, you know, this one, all that heat is at that boundary, and this one you have that really hot area in between the stud, the ferrule, and the plate, and all that heat is being dissipated out in either directions. So I wanted to look at just how is this thing melting during the heating and the cooling process. So what this is are steps and times using the boundary heat source model. So this is 0.08 seconds, this is 0.16 seconds, this is right at the end of the weld, and then this is a little bit into cooling. And then I changed the temperature regions for the contour plot to just be those during the melting phase of stainless steel. So all this little band here is the melting region of the stainless steel. So as you can see, as time moves forward, that melting region extends out further into the stud and into the target plate. And then once that's removed, this thing starts to cool down. So I looked into this a little bit further. I wanted to say, you know, how do the temperatures change radially across the base of the stud? So if you look just at the base of the stud, I took 3 points. So one at R equals 0, one at 0.05, which is about halfway, and one at 0.1, which is just before the edge of the stud. And you can see that these things heat up during the initial arc phase, and there's some melting occurring. And then once it's released, these things start to cool down. And if you notice, as you get closer to the edge of the stud and closer to the ceramic ferrule, that these things start to cool down just because these other pieces are taking on more heat. So this is good. This shows, you know, the melting that occurs, and it shows how quickly these things solidify, which shows the welding process itself. So then next, I wanted to ask myself, you know, how do the temperatures change in the Z direction to the target plate? So, you know, you're creating all this heat here, but how far into the target plate, what do the temperatures look like there? So I created 3 points. One is the corner at Z equals 0, which is the corner of the target plate. And then I went down to, made 2 points that are 0.1 and 0.2 inches into the target plate. And you can see that, you know, the further you go down into the plate, the less higher temperatures you see, but you're still getting some really hot steel here. So even, you know, almost a 1/4 inch into the plate, you're looking at 500 degrees Kelvin. So it's pretty hot. And just 0.1 inches from the top of the plate, you're at 800 Kelvin. So these calculations are interesting because you're looking at, you can use this to look at penetration depths, which I do in my paper. But a lot of the heat obviously goes down into this plate. So then I wanted to answer my question that I brought up about temperature sensitive material. So how far, if I go right off the target plate, you know, how hot are things getting over here? And what I found is that all the heat is being, you're seeing a lot of the heat vertically in this Z direction. A lot of the heat goes up into the stud, a lot of heat goes down into the target plate, like I showed on the previous slide. I made 2 points that were, you know, a 1/2 inch and 1 inch from the center of the stud. And even at, you know, a 1/2 inch, the temperatures here are only about 50, they're 320, around 320 Celsius, which is about 50 C. I'm sorry, 320 Kelvin, which are about 50 C. And there is a little discrepancy here, and I'm attributing that to the plasma region model. You know, you have this region that's a lot closer to the sides of the adjacent, the top of the plate. So if this thing heats up, it's obviously the conduction is going to go out a little bit further just because the heat source is a little bit further to the right. So that kind of confirmed what I was thinking. But basically what I found was using these models that the temperature along the target plate on the top of the plate, it really wasn't getting very hot, which shows that these studs that can be welded pretty close to adjacent temperature sensitive material. So that's good. So in conclusion, I created a thermal model that was made to mimic the stud welding using two methods. You have the boundary heat source method and the plasma region heat source method. Both models yielded similar results at the stud and the target plate, but differences were noted due to the increased hot zone of the plasma region, like I talked about. And this was really shown when we looked at the top of the plate adjacent to the weld. And heat increased rapidly in the Z direction, so that means up into the stud or down into the target plate, but heat did not increase rapidly radially, so the heat didn't conduct out radially into the plate as much as I expected. So that's good from a building perspective just because it allows us to put more temperature sensitive material close to the weld. So future work is I'd like to do some experiments to validate this model. We do stud welding all the time at EB, so my plan is to attach some thermocouples to some plates, have one of our guys weld a stud to it and see how those temperatures increase over time, especially on the adjacent to the studs and then on the underside of the target plate. I'd like to look at different studs diameters, different size studs. Obviously, you're putting more heat in at different size diameters in order to weld it, so that a lot of these results could change depending on how big your stud is. And I'd also like to look at the studs made from different materials. A lot of papers I found, they're starting to build techniques to use different metals both for the stud and the target plate. I think there's a lot of good things that could come out of that, especially at EB. I also, real quick, just wanted to say thank you to all the people that helped me through this project. Professor Ernesto, I really appreciate your help throughout this whole program. I couldn't have done it without you, so thanks.